All right, folks, let's take a look at what you got here. We've got this example problem where we have some plates that are held together by 4 1-inch diameter bolts, and you're asked to calculate the shear stress that might occur on those bolts. Now, first thing I'm going to do is, somebody asked the question, hey, don't the 100 kips here and here, don't they cancel out? Aren't they in equilibrium? And the answer is the whole connection's in equilibrium. I mean, you're not having this connection go this way or that way, but it's only in equilibrium. It's only held together because hopefully the shear stress is being generated by these bolts. In actuality, shear stress has to be developed at this plane over these 4 bolts, or else the bolts rip in half and the connection falls apart. I've got a little model here for you of just 2 bolts holding together 2 pieces of wood, but very similar to this. But I want you to think about that as I hand this around. I've loosened the bolts so you can actually think about, hey, these 2 pieces of wood are held together only by what the bolts are going through. And if these bolts are made out of styrofoam and I pulled on them, they'd shear right across this plane, right? Okay, so here's a little model that you just tug on and think about that. That 100 kips of ripping action has to be resisted by these 4 cross-sectional areas. Okay? So my stress, again, is load divided by area. It's 100 kips. And these are circular areas, so a lot of people say pi r squared for a circle. When you're dealing with bolts and whatnot, I like to say pi over 4d squared, just because bolts are always going to be given to you in diameters. They're not going to say the radius of the bolt is. Okay? So I got 4 of them, and each one has an area. Pi over 4 times diameter squared, which in our case is 1 squared. So I think that gives me a total area of all the bolts of 3.14 square inches, right? Okay, so 100 kips divided by 3.14 square inches gives me what? 31.8. 31.8. Okay, KSI, kips per square inch. Now again, is that a lot? I don't know. We have some steel bolts, certain grades of steel bolts that would handle that. We got other grades of steel bolts that wouldn't handle that. If you tried to handle that with like a bolt from Home Depot, a lag bolt or something, probably wouldn't handle that. If you tried to handle that with a piece of styrofoam, wouldn't handle it. So, and we're not worried about that right now, but what we're worried about is this. All right? So, any questions on that? Yes?
Why would the 2 forces in different directions not add together for a 200 force?
Because here's my model, right? I'm pulling on it this way with 100 kips. I got to have equilibrium and pull back. That plane right there is acted upon by a shear force. I mean, you can think of the bottom of this bolt just staying where it is, so that then that shear plane's acted upon by 100 kips pulling this way, or vice versa. Okay? All right, one other thing I wanted to talk to you about on this one. This is actually called a single shear connection. And it's called a single shear because when you look at a bolt, how many places in a bolt, one bolt, how many places are wanting to rip apart? 1. So there's 1 shear plane in each one of these bolts. There are 4 bolts, so there's 4 shear planes, 4 areas. What about if I had what we sometimes refer to as a three-plate connection. You know, where you have two outer plates held that are holding a middle plate or plates together. Okay, so really a three-plate connection is this. Just look at this: middle plate, two outer plates. All right. Well, when I pull on this, you know, if I pull with 50 kips of force that way, I must have to pull back with 50 kips of force this way, right, to maintain equilibrium. All right? How much would the outer plates typically hold? The middle plate's pulling with 50. Yeah, 25 each. You typically like the outer plates to be the same size so they hold the same amount of force. But this is a little bit different because when I look at these bolts in here, you know, and they want to do the same thing. If they don't, then we have failure. But how many shear planes do I have per bolt now? Huh? 2 each. So this is called a double shear condition or a double shear connection. So I mean, you can see this, you pull it out, you can say, hey, there's actually 2 planes for each bolt. Okay, and I'll pass this one around so you can see that. If there's 2 planes per bolt, would the connection be, would the bolts be stronger? Would the connection be stronger? Would it be weaker? Stronger? Well, what if? But if the same force was what?
Force in half would make the connection stronger.
If you've got more areas, then your shear is going to go down.
Okay, if you have more area, your shear stress is going to go down. So that's the right answer. Okay, so shear stress, because there's more area, because now every bolt is resisting. If a bolt was going to break, it'd have to break over 2 places. Okay, and since there's twice as much area, the shear stress goes down, so therefore it's a stronger connection. I mean, you could get by maybe with fewer bolts, okay, but that's the way to think of it. So there are what we call single shear connections and double shear connections.